P5, how particles interact. I'm actually making this video into a revision video really, so if you're looking at it straight after doing lesson 5, some of what I say might not make much sense to you. So if that's the case, I'd suggest you come back to this one after doing a few more lessons. Okay, because I'm going to concentrate on Feynman diagrams, but there are a few things I want to talk about that you may not have studied yet. So be patient. Now, it turns out there are 4 forces of nature which bind the whole universe together. So we make them into a table. We have the force in the first column. In the second column, we've got something called the carrier particle. So the idea here is that each force is mediated or made to happen, if you like, by a particle, a virtual particle called a carrier particle. So the first force, and the one we're probably most aware of in our everyday life, is the electromagnetic force. And the particle for that is called a photon, just like we're used to using photons as particles of light, but it turns out they're also used to carry the electromagnetic force, and the symbol is a gamma symbol. We've then got the strong nuclear force, which binds the nucleus together and stops all those protons bursting apart. And the carrier particle for that is called a gluon, and the symbol is G. We've then got the weak nuclear force, which is perhaps the most complicated and also the most interesting in this part of the course. There are 3 particles for that. There's the W+, the W-, and the Z0 boson. We're only interested in the 2 W bosons at the moment, but I'm just putting the Z in for completeness. The 4th force is gravitational force, which is very, very weak, and we think that that is mediated or carried by a particle we call a graviton, and physicists at the moment are trying to prove whether there is such a thing as a graviton, whether we can prove that it exists. So let's take the electromagnetic force first of all, and we're going to look at something called a Feynman diagram. And the first thing to note about a Feynman diagram is that there's a time axis. So time, in the ones I'm going to draw, moves up the page. So particles start off at the bottom and move up to the top as time passes. So electromagnetic, let's say we have a proton meeting another proton. They, as you can imagine, will repel each other, and the way we draw that with a Feynman diagram is to say that they exchange a gamma photon, and the photon is represented by a wiggly line, and push each other apart. Okay, so the two protons that went in have changed direction because they've been repelled by each other. You could obviously also draw the same diagram pretty much for an electron. Okay, so they also repel and they also exchange photons. Now the more interesting force is the weak nuclear when it comes to Feynman diagrams. So there are far more possibilities. So let's start with beta decay. This is the most common. Now in beta decay, a neutron turns into a proton in the nucleus. In order to do that, the neutron, of course, has no charge, whereas the proton has positive charge. So the thing that's got to happen to the neutron is it's got to get rid of some negative charge in order to end up positive. Okay, so it emits a W boson. So remember, the W's can be either positive or negative. So if the neutron has got to lose some negative charge, that means the W boson must be negative. Just think about that again. So neutron, to turn into a proton with positive charge, must lose some negative charge. So off it goes. The W boson is very short-lived and very quickly decays into an electron. So the electron is the bit that carries the negative charge, so the minus here ends up as the electron. But we also get another particle, which is the neutrino, and in this case it's an anti-neutrino. Now, in Feynman diagrams, lepton number and baryon number are conserved at every junction. So we started off with a baryon, which is a neutron. So one baryon went in to this junction here. One baryon must come out. So the proton is a baryon as well. So that works. Charge is conserved. Okay, so we've got neutral going in and a positive and a negative coming out. So positive plus negative is nothing, so that works. Okay, so this junction, charge is conserved and baryon number is conserved. At this junction, there are no particles going in, but we've got two leptons coming out. So we've got an electron and a neutrino, an anti-neutrino. So the reason this is an anti-neutrino is because the lepton number must be conserved. So no leptons went in. We've got a lepton number of +1 for the electron because it's a normal particle, and a lepton number of -1 for the antineutrino because it's an antiparticle. So +1, -1, add up to nothing. So lepton number is conserved. And you can also see that charge is conserved because you had a negative charge going in, a negative charge coming out. That may all sound a bit complicated, but so play it a few times through and see whether you're okay with it. Okay, another weak nuclear interaction is beta plus decay. So this is where a proton in the nucleus turns into a neutron. So we've got a proton with a baryon number of 1 turns into a neutron, also with a baryon number of 1, so that's okay. But to do that, it's got to lose some charge. So it emits a W boson, and the proton's got to get rid of some positive charge in order to turn into a neutron. So, not too surprisingly, the W boson has a positive charge and carries the charge away. That will turn into an electron, and because the W was carrying positive charge, this electron is actually a positron because it ends up with the positive charge. And we also get a neutrino because at this junction there are no leptons going in, so we need a lepton and an anti-lepton coming out. Now the positron is an anti-lepton. Remember, that's the only antiparticle that's got its own name, a positron. All the other ones are just anti-some, whatever it is. So we've got an antiparticle here, an anti-lepton with a lepton number of -1, and a normal neutrino with a lepton number of +1. So no leptons went in, and -1 +1 makes 0 as well. So at this junction, charge is conserved and lepton number is conserved. Next one, another weak nuclear one. We have electron capture. So this is where a proton in the nucleus captures one of the inner shell electrons in the atom. So the proton can only turn into a neutron, so you're safe there. Whichever diagram you ask to draw on this side, if it involves the weak nuclear force, you've got to have a baryon going in and a baryon coming out. So proton turns into neutron. At this junction, baryon number is conserved. 1 goes in, 1 goes out. This W boson has got to carry the charge that has to be taken away. So obviously the proton's got to lose its charge, and therefore it's a W plus boson. Now into this junction here we've now got some positive charge and some negative charge, so what comes out is a neutrino which has no charge. So if we think about the lepton numbers at this junction, we've got a lepton number of +1 going in, that's the electron, and a lepton number of +1 going out, which is a normal neutrino. So no antiparticles needed for that diagram. And another one. This one, we've got a neutron-neutrino interaction. This is very rare, but you never know when they might ask you about it. So we have a neutron interacting with an incoming neutrino. Again, a neutron can only turn into a proton, so we're safe here. Baryon number +1 going in, +1 coming out. Baryon number is conserved. But in order for a neutron to turn into a proton, it's got to get rid of some negative charge. So the W boson must carry away the negative charge. We've then got a W boson, which is negative, interacting with a neutrino, which has no charge. The neutrino turns into an electron. So the minus charge goes into the electron. The neutrino turns into the electron. So charge is conserved because one minus went in, one minus came out, and lepton number is conserved because one went in and one came out. Right, and another one. This time is a proton antineutrino. So it's the opposite of the previous one. So proton, again, can only turn into a neutron. In order to do so, its boson must be positive to carry away the positive charge. An antineutrino is captured, and it has no charge, so the lepton that comes out must be an anti-electron, a positron. So charge is conserved, +1 went in, +1 came out. Lepton number is conserved at the junction because an anti-lepton went in and an anti-lepton came out. And another one. This is muon decay. Now muon is the big brother of the electron. It's like an electron but about 200 times more massive. We get them in our upper atmosphere. So the symbol for a muon is the Greek letter mu. It's got a minus sign because it's just like an electron apart from its mass, and it's going to decay. They're very short-lived muons. So first of all, I think of it as getting rid of its mu-ness, so getting rid of some of its mass, I suppose. So we've got the muon has got a lepton number of +1 because it's in the electron family, and the neutrino, muon neutrino, also has a lepton number of +1, so lepton number is conserved at this junction. The neutrino has no charge and the muon has negative charge, so the W boson has got to be negative to take the charge away. And W bosons decay into electrons and an antineutrino, so that's the same as beta decay, basically. Okay, so that's muon decay. That's another possible one you might get shown. The one slight variation is beta decay again, but the quark picture. So a neutron can be represented as, in terms of its 3 quarks, so a neutron is an up, a down and a down quark. And in order to turn into a proton, which is an up, up, down, one of the down quarks has got to turn into an up quark. So these two are unchanged, so they're sort of drawn over at the side, and it's just this one we've got to worry about. But apart from that, the diagram is just the same as neutron into proton. in that the neutron's got to lose some negative charge to become a proton, so it's a negative, a W minus boson, and the rest of the diagram is exactly the same. The electron takes the charge, and to conserve lepton number we have an electron and an antineutrino. A couple of other things we've mentioned is pair production, so that's represented as a gamma photon turning into an electron and a positron. Notice they're not back to back in this picture, but that's because remember we've got the axis of time moving up that way, so they're sort of moving through time. The other very last one is annihilation, so that's drawn as electron meets positron, 2 gamma photons, and again they're not drawn quite back to back because they are moving through time. And I think that's all the Feynman diagrams they could ever ask you about.